Linux type convention, the X windows. All the OpenGL calls on X are preceded with GLX. And on OS X, we have the OS X graphics pipe. So GLX, OS X, WGL graphics pipe, all these are OpenGL graphics pipes. The difference is that they have different API calls to actually open the windows. And that's because OpenGL itself doesn't really define that. That's part of the operating system underneath it. There's one more. There's the OS Mesa graphics pipe. Mesa is, of course, a classic software-based implementation of OpenGL. OS Mesa is a pure software library provided by Mesa. So if it's an optional feature with Panda, you can compile with it if you've got it. And if you do, you get an OS Mesa graphics pipe, which entirely runs via software. And it's particularly handy to run on the server, for instance, where we don't necessarily want to take over the graphics card, don't even maybe have a graphics card. And it's nice when you got lots of CPU and just want to render simple things real quick. Let's see. So that being said, the graphics pipe, as I said, is just an abstraction to the particular kind of hardware you've got, or the particular kind of API you got. Particularly in the case of Windows, we have OpenGL versus DirectX. So the first thing you do when you start your Panda application is you have to create a graphics pipe. Now you've got this bewildering array of different kinds of graphics pipes. Most of the time you don't care, you just want something. So that's where the graphics pipe selection object comes in. Graphics pipe. This is a special class whose only function is to know about the different kind of graphics pipes there are and create one for you. And it looks in the config file, looks at the load display lines that you have, looks at the aux display lines that you have, and it has a few functions to basically give me a default graphics pipe. And you can also get one by name if you really want one, but typically you just want whatever the user has configured. So the first thing you do is create your graphics pipe selection and say, give me a graphics pipe, and it gives you one of these, and you don't care which one it gives you. This is what Showbase does. As soon as you import Showbase, it's going to create, well, you see it happen if you look at the code. Once you got your graphics pipe, you still don't have any graphics. All you can do with the graphics pipe is use it to create windows and buffers and the other things that you can actually render with. But even that you can't do directly. To actually do anything with a graphics pipe, you need, and this is a big whether the actual interface is a graphics engine. Now the graphics engine is an abstract thing. It doesn't know anything about the specific implementation of a particular hardware, but it is the owner of all the objects that you might create for that hardware. So typically your application will create one graphics engine and keep it around. There's got to be a global pointer. Panda doesn't create one for you. It's up to you to create it and be the owner of that pointer. Showbase does this again, for instance. That's base.graphics engine. And normally you don't need to muck with it. But once you have a graphics engine and a graphics pipe, you can use it to create a window. And the normal way you do that is with graphics engine dot make output. Make output is a general purpose function on graphics engine, and it can create windows or off-screen buffers of various kinds of parameters. And it's got a whole bunch of crazy parameters you can pass to it according to the kind of object you want it to create. And it tries to do some smart things. But for now, let's just talk about if you want to use it to create a window. And we'll talk about some of the cleverer things you can do with it when you're creating graphics buffers a little bit later. All right, so we've got a graphics engine, we've got a graphics pipe, and we use graphics engine.makeOutput. We pass it the pipe that we've got, and it will give us back a window. And the graphics window corresponds to an actual window on the screen with a title bar and everything. When we create the graphics window, we pass it window properties. And this is a simple structure that has the sorts of things that we might want to use to control the kind of window that we create. Whether it's actually got a title bar, where it is on the screen, how big it is, a few other interesting things like that. if you don't want to pass one into make output, you'll pass in a default value. And there's a default window properties which comes from your config file, and all these things you can set in the config file, like win size, normally just goes to the default window properties. But you can also override this on the fly and create your own window property structure and give it the sorts of things that you want to give it. Let's see. Furthermore, well, most of the window properties, when you create a window and give it the window properties, some of those window properties are burned in the window, cannot be changed. For instance, whether it's full screen or windowed, cannot be changed currently because of limitations in Panda. Other properties you can change. For instance, the title bar, with the text in the title bar, you can change that on the fly. The way you would change it would be to create a window property structure that has just a particular change that you want, and then call on your window object win.requestProperties. And then it won't actually change right away, but the next frame, it'll go around and apply that change. And the reason we have that one frame delay is because we want to be able to abstract out all the calls to the windowing system possibly in a separate thread. And that ties back into the ultimate design to have Panda control all the graphics calls in a remote thread, which according to, on different platforms, may or may not be thread safe. So we isolate the application programmer from the direct calls into the API. Okay. So now we've got a window. And we can have any number of windows. By default, ShareBase creates us just one. You can turn off that default if you set window type none in your config file. Then when you import ShareBase, you get nothing. And you have to call base.open main window to open your window yourself. Or you can call base.open window, which is basically going to do all this for you. You can look at the code. It's pretty simple. And it's going to create, it's already got a graphics engine, probably already got a graphics pipe. It's going to call make output with whatever window properties you give it and pass in a few default parameters. But even base.open window is kind of clumsy. It does some other things that maybe you don't want it to do. You can always just do it yourself if you just want a window. So now we got a window. Here's our pretty little window. We still can't render into it yet because we don't have a scene graph, we don't have a camera. All we've got is a big black window on the screen. Actually, it's worth pointing out, just the fact of calling make output returns us a graphics window. The window doesn't actually manifest necessarily right away, for the same reason that we have to call window properties through request properties. The window gets, although we've got a window property or a graphics window object, the window will actually manifest the first frame it gets rendered to. If we want it to manifest right now, we don't want to wait for it, you can call graphicsengine.openWindows. And that means stop whatever you're doing, don't return until you've opened the window, and then I've actually got a window on screen. But the reason that you wouldn't normally get a graphics window right away is because it's possible in a threaded environment that maybe the graphics engine is currently rendering some other frame into some other window at the time that you call open window, or the time you call create graphics window, and it's not available to create a window right now, so you have to wait for it. So open windows means stop and wait right now, however long it takes until you're done with whatever frame you're rendering, and then give me the window. Also, on implementations like Linux, when you create a window, it actually does require a round trip to the server, which might even be a different machine. So you still got to wait for that. Okay. We've got a window, it's just a black window. In order to render any content into the window, we need to have a display region. This is a further subdivision of the window. Typically, if you just want to render to the full window, you just want one big display region that covers the whole window. But in fact, you can create any number of display regions. And a display region is just a rectangular area of the window. It could be the full window, could be a part of the window, could overlap with other display regions if you wanted. The display region corresponds almost directly with the OpenGL viewport, if you're familiar with that concept. It's just a rectangular region into which you're going to start drawing stuff. When you create a window in ShareBase, it actually creates you 3 display regions right up front. You got one for render, which is your 3D scene graph. It also creates the second one stacked on top of that for render 2D, which is all your GUI. And it creates a third one called render 2DP, which I hardly ever use. But the fact that the display regions overlap is important because you have 2 different cameras that are rendering into the same scene in the case of render and render 2D. And you want your render 2D stuff to be rendered on top of all the 3D stuff. You could do more than that. If, for instance, if you wanted to have a side-by-side display with maybe you're doing a simple multiplayer game and you want to have person A over here and person B over here, you can create two side-by-side display regions and have completely isolated scene graphs, or with two different cameras in the same scene graph rendering to each display region. When you create a display region, you give it coordinates in the space 0 to 1. I believe it looks like this, where 0, 0 is down here and 1, 1 is up here, which just specifies the rectangular region that you want within the screen. It's a little unfortunate that we didn't choose -1 to 1, because that's the way that our mouse coordinate system goes. But we chose 0 to 1, and that's the way it is. It's a little bit different from the mouse. Now, got a display region, at least one, if we created it. And we're still not ready to render because we don't have a camera. So now you have to create a camera. A camera is just a Panda node, a specialized Panda node that is associated with a display region and has a lens associated. And now we're actually getting pretty close. So once you create a display region, and you can just create a camera on the fly. Oh yeah, in order to create a display region, you call GraphicsWindow.makeDisplayRegion. And pass in the coordinates of the display region you want, it returns your display region. The way to destroy a display region is just let go of it, because you're the owner of that reference count. As soon as the last reference to the display region goes away, it's gone. The way you create a camera is the way you create any other node. You just create it on the fly, you give it a name. It might have been called camera node to be consistent with other kinds of nodes like LED node or geom node, but it's just camera. And it's just a node. You can wrap a node path around it. So if you see, you create a camera and store your variable cam, you can put that inside a node path, and now you can reparent that to wherever you like. This is, for instance, what Showbase does. Base.cam is actually the node path to the camera that Showbase creates. But once you've created your camera, then you just have to call, I believe you call on your display region. You call set camera, and you pass it the node path to your camera. You don't pass it the camera directly, you actually pass the node path to the camera, because you might actually have multiple instances of your camera if you're just loopy in the head like that. And if you had multiple instances, that is, the camera has multiple parents, you might want to have one instance of your camera over here and another instance of the same camera for some reason over here. So you have your two different display regions actually have different instances of the same camera. That's just crazy. But and then you can do it. Because you can do it, we kind of have to support it. Otherwise, if you had multiple parents to your camera, Panda would just wig out as soon as you tried to render. So anyway, you pass a node path to your camera to the display region. And now, wham bang, you're actually rendering. Just by virtue of having a camera. Now, of course, if the camera is not in any scene graph, you're not going to render very much. It's not going to see anything. So you have to take your camera and parent it into some scene graph that's got some geometry in it. So let's imagine we have a scene graph. Now, a scene graph is really just a node with nodes under it. And in fact, in Showbase, it creates the famous scene graph render, which is just an empty node initially, and it's up to you to put stuff into it. So you can do that yourself if you wanted to. You can say render equals node path, and create some name render, for instance. Incidentally, the node path constructor that takes a string automatically creates a node with that name. If you don't pass anything to the node path, you've created an empty node path which references no nodes at all, which is different. But if we say node path equals, or render equals node path quote render, we just created an empty node called render, and ipso facto it's a scene graph. Now we can start parenting geometry to it. We could load models and parent them to our new render node path. And we can also take our camera here and parent that into render. Suppose this is our camera. Bang, suddenly we're rendering. So the pieces that all fill into place were, we opened a window, we created a display region. For that display region, we set the camera, and we assign the camera into the scene graph. Those are the pieces that we need to do to start rendering. And wham bang, suddenly we're starting to draw polygons, assuming we got polygons and they're somewhere in front of the camera. Okay? Yes?
Does it matter where the camera is in the scene graph?
It does in the sense that it inherits whatever transform you give it. So if there are transforms on this node and down here on this node, and you parent the camera down here, then that moves the camera and thus moves your point of view. The camera is now influenced by all these transforms up here. In OpenGL, there's not a concept of a camera in the same sense. There's a view transform, a world transform, which you give it every frame. Panda implicitly takes whatever transforms you accumulated on top of your camera and applies that to the world transform. So it's as if you've got a physical camera flying around in the world, and whatever the camera happens to be in front of is what you're going to see.
Question. When two display regions overlap, what controls which one is drawn on top?
Ah, God, there's my ringer again. Thank you. Right, so the display region has I've erased the display region, but the display region has a method called setSort. So within a window, when we draw the window, we draw all the display regions in increasing order of the sort value of the display region. If I've not specified a sort value, then the sort value is 0. And then the order is undefined. So in that case, I'd better not overlap my display regions because I don't know which one's going to come on top. When they do overlap, then the sort value makes a difference. So for instance, when ShareBase creates render and render 2D, it makes certain that it creates render 2D with a higher sort value than render, because we want render 2D to be on top. Since you brought up stacking the display regions, I should point out too that there are other important consequences to stacking display regions. In particular, there's something we don't think about too often, and that's the fact that before every frame we have to erase the contents of the frame before we start drawing to it. The OpenGL and DirectX both allow us to not do that. They don't do it implicitly, which is sometimes an advantage because you don't necessarily want to have to erase a frame repeatedly. But you do have to be able to know when to turn it on and when to turn it off. Now, the stupidest thing to do is erase a frame for every display region. That's OK, that works. And that's called clear. And there's also multiple things you can clear. You can clear the color, for instance, set it all to black or to a color of your choosing. You can also clear the Z buffer, and you can clear the stencil buffer. You can clear all those independently or not. Typically, you want to clear at least the color buffer and the Z buffer at the beginning of the frame for the entire window. If you're not overlapping any display regions, that's all you need to do. Just do it once and you're good. If you're overlapping some display regions, you may or may not want to clear the buffer, either of those buffers. For instance, in render 2D and render, we initially set it up so that render will clear both the color buffer and the Z buffer. Render 2D will then come along and clear the Z buffer only, but not the color buffer. If render 2D cleared the color buffer, it would exactly erase everything we just drawn in the render pass. So it's important that render 2D does not clear the color buffer because it completely obscures it. But it is important that it clears the Z buffer, because if it did not, and we wanted to render any 3D objects in render 2D, which we sometimes do, they might get obscured by crazy values left over in the Z buffer. Remember, the Z buffer is filled in as you draw things and corresponds to the depth in the scene of that thing that you drew. And if you then draw something from a different point of view in the same area, it's going to look strange when things just get occluded for no apparent reason. Now, in the early days of Panda, we used to avoid trying to do that second clear on render 2D, the Z buffer clear. We figured, well, the render 2D's purpose is to draw 2D stuff. We don't actually need to test the Z buffer. And that's an option too. You can just turn off the Z test, in which case you can just ignore the Z buffer altogether. And as you're drawing your polygons from render 2D, as long as they're just strictly two-dimensional and don't actually need to test the depth, it works fine. You can turn off the depth test. And that works as long as people never try to parent something like a tune head or some 3D object into your 2D panels. But as soon as somebody does that, it doesn't work, and nobody knows why, because the Z buffer is not there. So we finally gave up on trying to make that work and just said, OK, screw it. We'll clear the Z buffer. You can have the Z buffer in the 2D panel, and we'll just pay that slight extra cost for erasing the Z buffer twice. and actually, as it happens, gee whiz, we have to erase it 3 times because we have to erase it again for render 2DP. Ah, gee whiz.
What is render 2DP?
Render 2DP is an ugly word. The reason it exists is because it's difficult. Well, it exists mainly for this particular reason. If you want to put 3D objects in your 2D scene and have them overlaid on top of, well, let's see. I think it existed because here's the problem. We have render, a 3D scene. We have render 2D, which is 2D elements on top of that. We wanted to create a new display region within one of the panels that we opened up that would have 3D stuff within it. So we wanted to draw a little panel in render 2D and create a little rectangular region within that panel to have a 3D scene within it. That meant we would create a new display region right here, create a separate scene graph, put 3D stuff in it, all well and good, right? This is good until you have another dialog I want to pop up on top of that. Well, what are you going to do? So we had to have another layer of 2D scene graph because we have 3 layers of stacking now. We got the 3D scene in the background, we got a 2D scene on top of that, we have a 3D scene on top of that, and another 2D scene on top of that. That's why we have render 2DB. By default, it doesn't actually do anything. I think it doesn't get created unless you actually ask it to be created. So fortunately, most of the world doesn't have to deal with this, but we ask for it to be created, so we have to deal with it. Okay, did I lose anybody with the whole ZBuffer stuff? Okay. It's worth mentioning also, when we clear the color buffer, that's how we specify the background color of the window. I said by default you create the window as black. That's just because the default clear is black. Default clear can be any color you like. For instance, in preview, the default clear is gray. You can make it red, you can make it blue. When you call base.setBackgroundColor, it's actually calling into GraphicsWindow.setClearColor. And when you call GraphicsWindow.setClearColor, it's just specifying the particular color that you're going to clear to. And you can have a separate clear for the entire window, as well as for individual display regions. So one reason you might want to do this is because, well, as I pointed out, sometimes you do want to have a separate clear for each display region, especially if you've got nested display regions that layer on top of other ones. You might want to clear it again for that little tiny display region. But suppose you had, well, suppose we go back to our side-by-side display regions. Here, these guys don't overlap at all. We could clear just the display region here and then the display region here. And we do that by setting a clear on each of these display regions. But it's actually a little bit faster if we just clear the whole window, because graphics pipes like to do things all at once. So for that reason, you can have separate controls to clear the window as well as the individual display regions. By default, when you create a window, I think the window is set to clear itself and the display regions are not. But you can always tweak those individually. Okay. Let's see. Let me talk about also having multiple windows. I've said earlier you can call make output repeatedly and get more than one window. So we've got one little window here with 2 display regions. We can have another window, maybe a smaller one. Maybe it's got 4 display regions. I don't know. And when you do this, Panda will then draw to these 2 windows in sequence. And then within each window, it'll draw the display regions in sequence. Now, there's one more graphics object that I haven't yet mentioned, and that's the Graphics State Guardian. The Graphics State Guardian is so named because it is responsible for keeping track of what the current graphics state is, and issuing the minimal set of commands to the graphics API to change your graphics state, and also to draw all the vertices and stuff. So the Graphics State Guardian is a class that actually does the nuts and bolts of drawing to your window. And note, by the way, Graphics State Guardian is the abstract base class. There's a GL Graphics State Guardian and DirectX Graphics State Guardian and various flavors of Graphics State Guardian, which all comes out of the graphics pipe originally. Fundamentally, when you open a window, a graphics window with make output, it will create a graphics state guardian for you. And you normally don't have to think about it. The GSG, as we call it, will be responsible for just handling all the state that you need to do in order to render your scene. Sometimes you want to think about it when you're creating multiple windows. The reason that you want to think about it is because it might make sense for you to use the same GSG for both windows, or maybe you want to have a different GSG for both windows. Now, in practice, a lot of the interface inside Panda that handles this is not the most solid code right now. One of the things on our list is to rewrite all this and make it a lot stronger. But at the moment, as of April 2008, if you try to create multiple different GSGs and share them or use them on different windows, it doesn't work in DirectX, but it does work in OpenGL. On the other hand, if you're in OpenGL, I think the converse is true. So it's kind of a mess. So you're best off not messing with it. But I'll talk about what the intention is. The graphics state guardian isolates the render state. So that means all the textures, for instance, that get loaded to the graphics card and stored in HEP memory. The GSG is responsible for the GSG is responsible for copying those textures and knowing which textures are stored in the HEP memory. So if you've got two different windows that are rendering different views of the same scene and have the same objects with very many of the same textures, it probably makes sense to have just one GSG, because that way the same GSG can use the same textures to render to both windows. And when you do that, Panda will when you render the frame, it will load this window, set the GSG as a current graphics context to this window, and then render the display regions in order. And then it'll switch over to the next window and render its display regions in order. On the other hand, maybe you've got two different windows and they're not rendering the same thing at all, and furthermore, you've got two different graphics cards in your box and they happen to have a multi-threading capability so that you know you can render to both of them simultaneously. Then you might want to have a different GSG for both one. And you could, if you could take advantage of Panda's theoretical pipelining, you could actually render to each GSG simultaneously in different threads, and theoretically maximize their parallelism on your two different graphics cards without having to take advantage of any fancy graphics driver tricks. Because you'd be issuing completely different sets of graphics commands to each different graphics card, and that'd be pretty swell. When you call make output, one of the parameters you can pass in is an optional GSG, and you can pass it in from your existing window if you want to share the GSG. Typically, I think you're best off just letting that default to whatever it is. Okay, does that make sense? Okay. You go back to the display region a bit. Actually, let me talk about the camera just a little bit more. There's one more detail about the camera that I glossed over too. The camera, as I said, is associated with the display region. It's just a node. It has one more detail, which is a lens. When you create a camera, it has a default lens assigned to it, which is just a perspective lens. I think it's maybe 60 degrees wide, or actually maybe the width of the default lens comes from your config file. Also, the near and the far plane come from your config file. By default, I think the default near plane, or the default far plane, is really pretty close in. So a lot of people complain that they create a default scene and they can't see anything because it's just beyond the far plane. Well, these are all properties of the lens. And you can modify the properties on the default lens, or you can create a new lens. And there are several different kinds of lens. The most common one is the perspective lens. You've also got the orthographic lens. So these two together are by far the two most common lenses. Perspective lens is what we've got on render, and the orthographic lens is what we've got on render 2D. Perspective lens is typically used for rendering 3D scenes, and it has the normal properties like an angular field of view, It does, I mean, with a perspective lens, you get perspective foreshortening, such that things in the foreground, things in the foreground are bigger than things in the background. So with an extreme perspective lens, your cube looks something like this. If you have an orthographic lens, that's not true. Everything is exactly parallel. Parallel lines don't meet at infinity in an orthographic lens. So your cube always looks more like that, where these lines are all the same length. You can use your orthographic lens to render your 3D scene. It's kind of weird if you're flying around with an orthographic lens, because as you come closer to things, they don't get any bigger. So I've done this before. You set your render to orthographic lens and try to walk. It's just strange because you walk towards a wall and you feel like you're not moving, and suddenly you're on the other side of the wall. Similarly, you could put a perspective lens on render 2D, but then it's kind of weird because as things are further away from the camera, according to your Z value, which you normally don't think about in render 2D, they get smaller. So typically, orthographic makes sense for render 2D, where you just want to think about this particular plane of the screen, and you don't care about the depth into the screen. And the perspective lens makes sense when you're thinking about a 3D world. This perspective lens has all sorts of fancy properties. It tries to emulate the properties of a physical lens, a physical camera lens. So you can set the focal length of the camera, the focal length of a lens, in terms of 35mm camera, for instance, if you want. In order to do that, though, you have to set your film size to be whatever the film size of a 35mm camera. I think it's like 25.4mm this way and something else this way. I mean, a 35mm camera has film like this with sprocket holes, and this whole distance is 35mm. But the film size itself is something a little bit smaller. So on the lens, you can set the film size, which means you set the theoretical size of whatever magical film you got inside your camera. And that determines the units that your focal length means. So if you set your film size in millimeters, then you can set your focal length in millimeters, and that automatically sets the angle of view of your lens according to the normal perspective ratio. If you wanted to set these in inches, you could do that, and then you have to set your focal length in inches. It amounts to the same thing. Or conversely, you can just set the field of view directly as an angle. In fact, there are the three functions on the lens, which are set field of view, set film size, and set focal length. Those three interplay. When you set any two of them, it automatically computes the third. So if you wanted to, you could set your film size and set your angle of view, and it would tell you what your focal length is. Yes?
How did you differentiate vertical and horizontal field of view, or is it circular or something?
When you set the field of view, you can specify the vertical and horizontal separately. Or you can set the horizontal, and it will compute the vertical based on your stated aspect ratio. That's basically how it comes down to. So yeah, in the perspective computation, you want to compute the vertical and the horizontal field of views independently. It does make a bit of a difference. Actually, there's a family of other lenses too, which you cannot use in real-time rendering because the hardware doesn't support it. But there's also fisheye lens and cylindrical lens and some other fancy lenses that have other mathematical properties. But they're not linear, which is to say they can't be represented in a linear 4x4 matrix. So there's no way you can pass them into OpenGL-DirectX. But it might be possible to write a shader that could do something fancy like that. It'd have to have some way to pass those fancy parameters, and we don't have any such hookups right now. But we can use those for something called the nonlinear renderer, something like that, which is actually a poor man's way to do fancy fisheye tricks in Panda. And that's a topic for a different lecture. But in some of those fancier lenses, you can specify things like field of view and polar coordinates. But for a normal perspective lens, you have horizontal and vertical field of view. Okay. One other thing you can do with a lens is you can actually rotate the lens. Normally, by default, the lens is looking straight down the y-axis, which is by Panda's convention forward. You can actually rotate the lens to look any direction other than that, which is kind of akin to taking your camera and bending the lens to point in some other direction. The camera is still facing forward, but the lens is looking off in another direction. This can be confusing, but the main reason you want to do this is to implement maybe a cave type environment where you have multiple display screens around you. And you have one camera that looks forward, one in each direction on the sides, and you just want to have one camera that you position in the middle, and it has multiple lenses that point in different directions. And that's kind of convenient for that reason. And there's another reason that you want to do that, and that's for stereoscopic cameras, where you have the left and the right eye that look in slightly different directions. It's convenient to have one lens that looks one way and one lens that looks the other way. And you can do that explicitly, or you can also do that. There's also functions within perspective lens to implicitly set up a left-right eye pair. And I'll talk about those towards the end of the lecture if we have time. Okay? So look at you. You've got a graphics window, you've got display regions, you've got the camera, you've got your lens. You're cooking. Now let's see. What we want to do next is do off-screen rendering so that we can really do some of these fancy graphics rendering tricks. Working into that, let me talk about saving the screenshot. One thing you typically want to do frequently in any game is save a screenshot of the current image. I mean, users like to do that, and sometimes there are game-related reasons to do that. There's a call on either graphics output, graphics window that is, or on individual display regions to save the screenshot. You can call it just displayRegion.SaveScreenshot. You can give it a file name. It'll save the screenshot to a file name. You can also create a PNM image, which is Panda's internal memory image. Create an empty one of these and pass it into getDisplayRegion, or getScreenshot rather, and it will fill in with the pixels of your display region. So you can use this to fill in, if you've got a small display region, you can capture just that portion of the screen. Or if you've got a larger one, you can capture the larger screen. Now this is captured at the end of the frame. So if you happen to have overlapping display regions, and suppose this one is underneath and this one is laid on top of it, so that when this one draws, it erases this corner of the smaller one. If you then take the smaller one and try to save the screenshot, it's only going to get this amount of the smaller one, and this corner of it will have already been filled in with the new one. It's just something to be aware of. So save screenshot works by querying OpenGL read pixels, I think is a normal call, and it just copies those pixels from the frame buffer memory into system RAM. A relatively expensive call, but for purposes of the screenshot, it's not too bad. You could, in principle, do this every frame. You could, every frame, call getScreenshot, copy it to a PNM image, and then use that PNM image to load up a texture, and then apply that texture into your scene. That's, of course, a real slow way to do it. But, at least it's easy to understand how it works. And if you do that, then you can have a camera that walks around through your scene, and you can apply the view of that camera onto some texture and do whatever fancy effects you want to do with that. But there are, of course, ways to do that more implicitly inside the graphics view. And that's where we come into off-screen buffers. So is everybody with me so far? Okay. Now we've got a graphics window class. Graphics window actually is a specialization of a base class, which is graphics output. Most of the methods that I talked about in graphics window are actually methods on graphics output. Graphics window only adds the things about window properties and things like that, setting the title bar and properties like that. Graphics output has all the meat about actually rendering to the thing. It has things like set, clear color, and create display region, and things like that. Another child of graphics output is GraphicsBuffer. Excuse me a second. Okay, GraphicsBuffer therefore inherits the interesting things of graphics output, except that it never appears on screen. So when you call GraphicsEngine.makeOutput, another funny parameter you can pass it will tell it to create your graphics buffer instead of a graphics window. And you can use this graphics buffer to exactly the same way you render to a graphics window, except that you're never going to see it. Now, there's not much point in doing that unless you plan to apply the output of this to a texture and take that texture and put it in your scene. I guess you could use it to do some off-screen rendering and save it to a file. But most of the time when you create a graphics buffer, you're going to do some real-time rendering with another texture. The easiest way to get a graphics buffer into a texture is to take your graphics window object, which, for instance, suppose it's base.win, which is the default graphics window object, of course, and you call make texture buffer. Make texture buffer is actually just a thin wrapper around GraphicsEngine.makeOutput, but it passes in the appropriate parameters to graphics output to create you a graphics buffer, and it returns that. And furthermore, this graphics buffer is already set up to be appropriate for rendering off-screen a texture that will be applied to some scene that base window sees. And I'll talk a little bit about exactly what that means. But this is the way that most people create an off-screen buffer. But this is just a buffer. You still have to create a display region and a camera and set that camera in a scene and start rendering. The scene could be the same scene as render. So maybe you're doing something simple like you just want to have a little spy camera on that displays a scene on a little TV in your scene. Create a little TV model and you have a screen on that TV. You just want to apply to that screen just the texture that is output from your spy camera that you create. So you call base.win.makeTextureBuffer. It creates this off-screen little buffer that you're never going to see. You set up a camera for it, and you put that camera in the scene wherever your spy camera is going to be. And then you say buff.getTexture. And this returns a texture that corresponds to the output that is rendered from this off-screen buffer. Then you can just take this texture, just an ordinary texture like anything else, and apply it to anything in your scene, and that thing is colorable according to the output of your buffer. Now, what's actually happening might be any number of different things. According to the hardware capabilities of your graphics driver, according to the Panda's capabilities, you may or may not be rendering directly into a texture. You might be rendering to a separate memory of off-screen buffer and then copying to a texture. Or you might even be rendering into your main window and then copying from there to your texture. When you get back a graphics buffer, I said that it might be any number of, well, just like a graphics window. It could be a GL graphics buffer, a DX graphics buffer. We've actually got, of course, there's the DX graphics buffer and the GL graphics buffer. In GL, DirectX is actually pretty sane with their off-screen graphics buffers. GL is actually pretty crazy because there's at least 3 different implementations with different kinds of graphics buffers. There's a WGL graphics buffer, and there's a GLX graphics buffer. And these both exist because under Windows and under Linux, there were 2 different APIs to create a graphics buffer, because originally OpenGL didn't have a way to create an off-screen buffer, just like it doesn't have a way to create Windows. But later, the OpenGL consortium said this is just crazy. So they came up with a standard OpenGL way to create a graphics buffer that has nothing to do with your operating system. And that's the new GL graphics buffer. But according to how new your drivers are, you may not have this available to you. So in that case, if you're running on Windows, Panda is going to first try to create, assuming you're using OpenGL, Panda is first going to try to create a GL graphics buffer for you. If that doesn't work, it's going to try to create a WGL graphics buffer. That might fail too, in which case it falls back to a parasite buffer. Now, if you're running on DirectX, it's a lot simpler because there's only the one possibility. So the first thing it tries to do is create a DX graphics buffer, if that exists. And if for some reason that fails, then again it'll fall back to the parasite buffer. And it's possible to configure Panda to try to create a parasite buffer first before it tries the others. Now, a parasite buffer is a funny thing. It's not actually a graphics buffer at all. All it is a pointer onto your main window. So remember, we called base.win.makeTextureBuffer. That means I can use base.win to create a parasite buffer if I need to. And if it creates a parasite buffer, it's going to, before it draws the main scene of your window, it's going to draw your buffer into the main window, where if you didn't do anything else, it would become visible. But the theory is that you're going to draw into this main window and take advantage of the pixels there, and then you can copy them out into your texture after you've drawn it. And then by the time you're ready to draw your main scene, you can do the clear, and it'll clear out that whatever you've drawn, and you can draw safely as if it was never there in the first place. And so you end up with an invisible buffer that's there that you didn't really, you don't even necessarily know that it's there at all. And that works pretty well when the graphics buffers can't be created for various reasons. It does have limitations. I mean, one obvious problem is that parasite buffer can't be any bigger than the window itself. So if you ask for a 1024 by 1024 graphics buffer, and you happen to be running on a laptop that's only 1024 by 768, well, too bad, you're not going to get that buffer. In that case, Panda will automatically downgrade the size of your buffer, and you might want to be prepared to deal with that. Another problem, too, is, well, if somebody resizes a window after you've created it, oh dear. That's problems too. That makes it even worse. But for the most part, a parasite buffer works pretty well. As we discovered last week, it's important to keep those sort values correct, particularly when you might have parasite buffers, because normally, as I remember before, when we had multiple windows, if you got multiple windows rendering with multiple display regions in each one, Panda will render one window, all the display regions in that window, then move on to the next window. Same thing happens with buffers. If you have off-screen buffers, Panda will render a buffer, render all whatever display region that buffer has, then move on to the next buffer or the next window, render all the buffers or display regions in that one, and move on. And this all depends on the sort value that is set on the window or the buffer. Now this is different from the sort value on the display region. There's a sort value on the display regions that control the order within that particular window or buffer of those particular display regions. But there's also a sort value on each individual window or buffer. And it's important to get those correct when you're having multiple windows that all rely on each other. So if you have one scene in your off-screen buffer that's going to render a texture that you then intend to apply to an object that will be rendered in your main scene, it's obviously important that you render that buffer first. And that means that you need to set a sort value on that buffer that is lower than the sort value of the window that's going to render that texture. Now when you call makeTextureBuffer, it does this. By default, it will create you a buffer whose sort value is one less than whatever this window was. So the window is typically 0. This means it gives you a buffer whose sort value is -1, and that's OK. But you might play games with the sort value later. You might then set the sort value to something else without realizing that you've just broken your buffer. So you have to be aware of that. And also, it's particularly egregious if you have a parasite buffer. If you have a proper off-screen buffer, you may not notice if you're off by 1 frame. If you render to your off-screen buffer, if for instance you happen to render to your main window first, and then render to your off-screen buffer second, well, it's going to be, the texture that you rendered the first frame is going to be blank. The texture you rendered the second frame is going to be the first frame's texture. You probably won't notice unless you have some real fast-moving action. But if you have a parasite buffer, if your off-screen buffer actually happens to be a parasite buffer, you're going to notice that, because it's going to render your main window, and then it's going to render your parasite buffer on top of it. OK. So we got a main window. We got a buffer. And if we call it base.win.makeTextureBuffer, we're going to have a texture associated with it. We can apply that texture. Now, the way that the texture is actually associated is decided by Panda internally according to the best way they can do it. Preferably, Panda will have created a DXGraphicsBuffer or a GLGraphicsBuffer, and it will be able to associate that buffer directly to a texture. So that means when you render to that buffer, it is actually directly rendering into texture memory. Then when you apply that texture, it's using that same memory that you just rendered into. Modern graphics cards can do this pretty well. If you've got an older driver or an older graphics card that can't do that, then it falls back to choice B, which is create one of these buffers, and then at the end of the frame, automatically copy it using an OpenGL DirectX call into your texture buffer. And that's not so bad either, because the copy still happens entirely on the graphics card. doesn't actually have to copy the bits onto your CPU. So it's still pretty quick. Particularly, this is what happens on the parasite buffer, because again, obviously, when we're rendering in the same frame as our main window, we can't use that same texture, the same pixels to be our texture, because these pixels are part of the main frame buffer. So we have to copy them separately into another texture elsewhere. And then when we clear the screen and draw it again, we have the texture available. Now, the worst possible thing to do is to copy the pixels all the way to system RAM, because that's extremely slow. But that's an option. When you call make texture buffer, there is one parameter, an optional parameter called toRAM. And if by default that's false, but if you pass toRAM true, then it will every frame copy the contents of the buffer to the system RAM, so that when you look at your texture object, you actually have those pixels available to you in system RAM. Normally, you wouldn't want to do that for normal graphics effects. But there are sometimes that you want to do that. For instance, if you intend to save that texture image to disk, you'll need to do that. If you intend to do any CPU processing on the texture image and you don't particularly care how slow it is, well, you need to have the pixels in RAM, so that you need to do it in that case. As a case in point, there is a function on Showbase called saveCubeMap. And you can call base.saveCubeMap. And basically, what it's going to do is create a default camera with 6 cameras looking in the 6 different directions of the cube map, render 6 different textures out, and save them all as 6 different images. That's a pretty easy way to do it. There's also a function called base.saveSphereMap, which takes the same trick. Remember, a sphere map is similar to a cube map. It's an older technology, but it takes all the 6 images of the cube map and boils them down into one spherical image. Base.saveSphereMap starts with a cube map, takes its 6 pictures, and then does some further image processing to turn them into one spherical picture, and saves that out. So that's a fine example of when you want to do toRAM equals true. It's worth pointing out, too, that actually for the purpose of getting out a texture, normally we're just talking about a 2D texture that you're getting out from the display region. But it's possible to get out a live cube map rendered the same way that we render it to the normal texture. And Panda can render to the different faces of the cube map directly, the same way it can render to the single 2D texture. In order to make that work, you need to have 6 display regions. Each display region is associated with the same buffer. And there's a separate method on display region called setCubeMapIndex. And when you call that, you call it 6 times on the 6 different display regions and set each one to a different cube map index, and set a different camera for each display region. And that's basically what base.saveCubeMap is doing. It creates 6 display regions with 6 cameras, sets each one to a different cube map index. And then you create a cube map texture with your texture buffer, and it actually renders out to the different 6 different faces. And then you can render that cube map on your scene in real time without having to copy the CPU. Okay, how are we doing?
When would you do that, for example?
Well, if you wanted to do real-time reflection, this is a commonly done trick. You put a cube map camera in your scene, rendering out the 6 different views in 6 different directions, getting basically the whole world. And you can take the output of that and apply it as a cube map to an object in your scene, in the same scene. And then you're basically applying real-time reflections onto that object. It can be slow if you do it poorly, because you're rendering the scene basically 7 times now. But if you're clever and you minimize the geometry that gets seen by the cube map camera, you can do pretty well.
Is that what you're doing for the seas and pirates?
No, it's not a cube map.
Okay.
But it's a similar trick because we do have a separate camera. It's just a 2D view. In Pirates, we have there's the plane of the sea, and we have the regular camera which is looking down on it or wherever it is. It's easy to compute the reflection vector, and we have a reflection camera that's the mirror image of that camera looking down in the same direction. And that just renders a 2D view, which we then apply the same to the polygons. a sphere map or a cube map makes more sense when you want to have reflections onto a solid object rather than reflections of a whole world on a plane. So like you want to have a shiny car or something like that. Okay, I think we're almost out of time because I heard the clock chime. I was going to talk about stereo cameras. I guess I can talk about that until we run out of time. Okay. I mentioned this just briefly. Let's see. Display region. Well, let me go back to the lens first. When you create a lens, you can specify one of three properties, or you can specify one of three settings on the lens. You can be the default lens is a mono lens, which is just regular old lens. You can also say this is a left eye, or you can say it's a right eye. And if you do that, then it automatically configures the lens according to the interocular distance that you set on the lens and the convergence distance. You can set these two properties on the lens. So looking down from the top view, let's say we've got a camera that would be looking here and looks this way. We can specify an interocular distance and a convergence distance. My poor camera views. So the interocular distance is basically the distance between the left and the right eyes, and the convergence distance is the distance at which the two eyes are looking. So normally when you have binocular vision, you have two eyes that are offset by some distance, and they're converged just a little bit together. You can specify these two parameters on the lens, and if you have just a default mono lens, they mean nothing, because the lens is going to ignore that and look straight down the center. But if you have either a left eye or a right eye lens, setting these two distances configure which way the lens is going to look. So you could do this. You could create two different display regions. For instance, suppose you wanted to create a stereoscopic vision with side-by-side images. You could create a left image and a right image, set two different cameras on both of them with the same lens. No, I'm sorry. You would have two different lenses that are identical lenses with the same distance, and you'd set left lens on the left one and right lens on the right one, and then you have two side-by-side views. And then if you had a output device that would output this to two halves of a stereo camera, or maybe two halves of shot glasses or something like that, you'd be golden. Panda actually goes better than that. It allows you to create a single display region, which is a stereo display region. OpenGL, and I think DirectX 9 supports this, but I know that OpenGL has always supported the idea of a stereo display region. And modern graphics cards can actually render to a stereo output device with a stereo display region, and they can drive the shutter glasses and do all that work for you. So there's a third mode on your lens, which is, in addition to left or right or mono, I guess there's a fourth mode. You can set stereo, which means in this case we actually set the same lens on the same display region. We just create one display region, which is a stereo display region. We set one camera on it. Panda will actually render this one twice. It knows that it's a stereo camera. It knows that it needs to render it once for the left eye and once for the right eye. And it pipes that to the graphics card both ways and tells the graphics card this is a left eye and this is a right eye. And the graphics card handles shuttering the glasses or whatever it needs to do to make that work. And there's a big advantage to letting Panda do it this way, because Panda then knows that you're rendering the two scenes that are very similar and in fact have the same camera. Panda can do an optimization, a cheap little optimization, where, remember, we talked a couple weeks ago about the way that Panda draws a scene. It traverses a scene graph doing what's called the cold traversal, in which case it looks, walks the entire scene graph, looks for everything that's in front of the camera, and throws away things that aren't in front of the camera, and also accumulates all the render state and basically gets the scene ready for rendering. In this case, where we have two separate display regions with two different cameras, Panda is going to have to do that traversal over the same scene twice, which is kind of unfortunate because these scenes are almost identical. If you give it a stereo camera, Panda knows that it can get away with just doing that traversal once, so it saves a considerable amount of time. It does have to broaden the field of view because your two left and right eyes aren't exactly seeing the same thing, so what it does is it broadens the total field of view to cover both of them. So you render a little bit more on the left eye than you might not have seen, and a little bit more on the right eye than you might not have seen, but on the whole it's a big savings. Yes?
So in stereo mode, does it take the same parameters in terms of how far apart the eyes are and the convergence length and everything like that?
Yes.
Okay.
Right, so this is all Right, in stereo mode, you've already set the interocular distance and the convergence distance. And it uses those parameters to set up the lens in left eye and right eye and just switches back and forth.
So stereo mode is not physically realistic if you have an option that's like right in front of one eye, for example. It wouldn't actually be represented properly. Or is that not true?
I'm not sure what you mean. So it's